My goal is to get that back to you by Monday. We'll see if that actually happens. It might be Wednesday, but hopefully it'll be kind of a good spot to kind of check, do we actually understand how to work with these problems? I think like it's kind of a deceptively simple problem. There's actually quite a few moving parts in something like that. So it should be a good check. Do you understand, like, how do we deal with pressure and velocities and forces and direction and all of these kinds of things? So we'll see how that goes. I'll try to get it back to you relatively soon. To start though, because I botched 30% of yesterday, or not yesterday, Wednesday, whenever that was. Why did so we had last time, right, we had this cart. I won't spend too long because I don't know, I was having, you ever have that where you like confuse yourself and then you have trouble thinking? So this is what I was trying to think about, and apparently it wasn't working. So we had a jet of water coming at the cart like this, and that is right there's would be our control volume, and the water is going out that way. The force balance on this system would be, so if we're letting this, if V equals a constant, so this was like the problem that we solved not Wednesday, but the previous time, right? We would get plus Rx equals the sum over our control surfaces of U rho D dot A, right? And when we solved it Monday, I guess, we said, well, pressure is zero. Pressure is atmospheric everywhere. So P, 1 atmosphere, Gx equals 0. There's no gravity in the x direction. So we were left with just this reaction force. That was the force that the scoop is pushing on the water. Then when so this is for a constant V cart. I guess the term we used, so that would be capital U, constant velocity of the cart. When we solved this then yesterday, well, not yesterday, I still can't talk. This is U cart. So when U cart is constant, this was the equation that we were left with. Okay. So what that means, there is a force which is pushing against the water, like precisely because the cart is not allowed to accelerate. So there has to be some force pushing to the left precisely because the cart is not allowed to accelerate. So there has to be, whether it's, I don't know, sticky wheels or something like that, because the jet's coming in at 30 and our cart was moving at 10. So if there is not a force, we would experience an acceleration. There must be a force because we're not experiencing acceleration. So Rx must be there because we'll call it a cart equals 0. So it has to be there because F equals ma has to be true. So there has to be a force resisting that acceleration, right? For acceleration to be 0. When we solved it then on Wednesday, now we let F dx plus Rx minus M cart AX cart equals sum over our control surfaces of U rho D dot A. So now this equals 0 for the same reason, right? We did this. This equals 0 because g of x equals 0. Now, here, our x equals 0 because no force is resisting CV acceleration. So the only thing kind of does that make more sense? Everything makes more sense than Wednesday. But hopefully this makes more sense why that went away. And I don't know, I got turned around in explaining this, but we had it in one case, Rx that's the reaction force. It has to be resisting acceleration because our control volume is not accelerating. So there has to be a force that's resisting. We're not really told where that comes from. I guess it would come from like the wheels, friction in the wheels, or air drag or something like that. There's some combination of forces. We don't know what they are, but they have to be resisting acceleration. Because otherwise, a 30 meter per second jet hitting something that's only going 10 is going to tend to make that thing accelerate. When we solved it the second time, so this is with now with acceleration. When we solved it the second time, we allowed our cart to accelerate. We said there is no friction, there is no drag, there is nothing that is resisting that motion. So that's why Rx went to 0. Does that make sense?
So since we're adding in the force balance side of it, we're adding the next.
Yeah, kind of because the acceleration is there.
Yeah. So
that's the kind of the key term, but it's because there are no forces resisting that acceleration. So if there were drag forces or friction or something like that, some other force that's resisting it, then that would go in Rx as a force that's acting on the control volume, pointing in whatever direction it happens to be pointing in. Okay. All right. So I wanted to make sure hopefully we're a little bit more on the same page with that, because I feel like we weren't even on a page on Wednesday. I don't know. Such is life. I guess sometimes it happens. Okay. So like we said on Wednesday, the one thing I stick to is that was the kind of wrapping up sort of Reynolds transport theorem. So let's think about what we can do and what we can't do. So what we can do is problems like you all just did. And even, more exciting ones like, you can figure out how fast a jet boat goes. You can figure out forces acting on some objects. So we can figure out and describe how the laws of physics work for fluids, for moving fluids. Which, when you think about it, that's right. That's a fairly powerful thing to be able to do. We can describe how kind of classical laws of physics, how they translate into this world of fluids moving. What we can't do, we don't yet I'll just leave it like that. We don't yet, oh, I hit a button. Stop it, stop it. This one, do that. Good, back to life. Okay, so what we can do is we can describe the laws of physics for fluids. What we can't do is really have any description of fluid flow. So if you think about it, every time that we have had to deal with what does fluid flow look like, what do velocity, like what is the velocity doing? We've always had to fall back on me just telling you. So for example, if I said, what is the flow inside of a pipe look like? You say, I don't know, you gave me an equation, let me use it. We can use it once we have the equation, but those equations are just magic and I gave them to you, right? So hopefully we're not comfortable with that, right? They're not just magic equations that I made up. They have to come from somewhere. So where do they come from? Well, they're going to come from the same laws of physics that we've just been talking about. But now what we're going to do, so here we're moving from, like if you're following along in the book, we're moving from chapter 4 into chapter 5. And in chapter 5, we're going to be looking at a differential analysis of fluid motion. So if you actually want to understand how fluids move, how this actually works, okay, what do you have to do? You have to not just look at kind of the bigger picture like we've been doing. That's important, certainly. But we have to like start zooming in and get smaller and smaller and smaller and take some of the same ideas that we've just used, because we've used how do physical laws apply to moving fluids, take those same ideas, but now shrink it down and get smaller and smaller and smaller until we're looking at each individual little drop of fluid and say, how do physical laws like F equals ma and conservation of mass, how do those apply to that one little individual drop that's surrounded by other drops, right? The one little drop inside of the, at this region, and how does it move, and how does conservation of mass work, and how does F equals ma work, and how do all these things work at like the individual little tiny particle of fluid level. So that's what we're going to do in chapter 5. I think it's kind of fun. Unfortunately, it's going to be a little bit, not unfortunately, we're engineers. Fortunately, it's going to be a little bit math intensive. So I'll try to, especially when we dive into the F equals ma thing, we're going to do some of it. I'll try to kind of hold your hand as we go along to make sure we don't get too lost in the math. I don't want you to get super lost in the math. We're not going to focus that heavily on it, other than because I think it's interesting and useful to understand a little bit where the math comes from. Because if you do anything with fluids, you're going to do stuff or hear about stuff related to the equations that we're going to derive, because it describes fluid flow. So if you want to know how fluids work, these are the equations that you use. So let's jump in. Let's jump in with conservation of mass first. So let's zoom in on a fluid particle. Okay, so we'll zoom in on a fluid particle. We'll put some axes there. So that's going to be, we'll make it a cubic fluid particle, because that's the easiest to do some of our math with. But we'll make, okay, so a fluid particle like this. This is X, this is Y, this is Z. And we're going to make it really, really small. So how big is it on each side? Well, it's a differential length. We're going to zoom in, it's going to be super tiny. So this dimension here is, the X dimension is dx, the Y dimension is dy, and the Z dimension is dz. Okay, so those are the sides of our cube, dx, dy, and dz. Those are the edge lengths. This is our, right? This is now our control volume. In some, okay, so this fluid, this is a little tiny region of space. inside of some moving fluid. So the fluid is moving, and we're just zooming in on this little tiny region of space, using that as our control volume. So the fluid around it is moving arbitrarily. I don't know how it's moving. So the velocity field is V, which is U I hat plus little v j hat plus w k hat. So that is kind of just some arbitrary velocity field. I don't know. Maybe it's changing with time. Maybe it's changing with space. I have no idea. It's just the velocity field. If we want to know conservation of mass on this little tiny control volume, we would use Reynolds transport theorem. So let's do that and see what happens. So use Reynolds transport theorem for conservation of mass. All right, so Reynolds transport theorem, that would be 0 equals dt over our control volume of rho d volume rho v dot d a. Okay, so we have two terms here. Right, the 0 is still going to stay 0. This first term and this second term. So let's look at each of those individually and do that on our little, really small control volume. So let's first look at this first term. So this is going to be d dt, the integral over our control volume of rho d v. Okay, that is going to be equal to, okay, what is a differential volume? What is the volume of our little, right? It's dx, dy, dz. So that's our differential volume. That's the volume of our little cube. And presumably the density could change depending on exactly where we are. So this is going to be equal to d dt of rho dx dy dz, right? It's going to be just equal to the density times the volume. Presumably the density could change with time, but the size of our cube is not changing with time. So that's going to be like the dx, dy, dz parts, those are all constant. It's just the density that might change with time. So this equals d rho dt times dx, dy, dz. Right, another way to think about that, how does mass change with time inside of our control volume? It's related to just how the density changes with time, times the volume. Okay, the second term here is for flow in and out. So this term, integral over our control surfaces of rho v dot dA. Okay, so let's look, we'll just look at the x direction. Let's look at x. So in the x direction, we have, you know, this side of the cube, which is, this is dy, this is dz. And we have this side of the cube here. Okay, and this distance here is dx. So we're just looking at that. There's going to be a velocity in and a velocity out. The velocity in the x direction is u. So this has a velocity, we'll call it ux, and it has a density ux. The subscript x just means it's at that side, at side x. So this is position, we'll call this position x, and this is position x plus dx, right? Another little bit further down. So this other side has maybe a new velocity, maybe the velocity's changed, whatever it happens to be, and maybe the density has changed too. So density x plus dx. So now this is where things get a little strange. So we can say, okay, how does the velocity, say at the right-hand side, how does that look compared to the velocity at the left-hand side? Well, it's going to be, if you're coming in at, say, 10 meters per second, and you speed up 1 meter per second, then you're leaving at 11 meters per second. So that's how we're going to relate the velocity in and the velocity out. How fast are we coming in? That's whatever it happens to be, ux. How much are we changing? And then that's going to be how fast we're leaving. So we can relate the in to the out. Both for velocity and density. So we'll say ux plus dx. So the velocity out is equal to the velocity in plus, and I'm going to write this in kind of a weird way. But all this is a funky way of writing du, right? The dx's could cancel each other out and you would just be left with du. I'm just writing it this weird way because it makes my life easier later. If you've taken heat transfer, you remember we did this pretty recently doing the heat diffusion equation. Okay, so we can do that with u. We can also do that with density. Density x plus the change in density with x times dx. Okay. So now we have to put this kind of together into the perspective of Reynolds transport theorem. So now put it back into our original equation, which was 0 equals, now our first part is going to be the change in density with time dx, dy, dz. The second part, okay, now we're doing the integral over the control surface. So we're going to have the density, we'll do first, I guess, the left side, and then we'll do the right side. So it's density, and then velocity dotted with the area. So that's going to get a negative sign. The area is dy dz. Right, so this is minus density x ux dy dz. Okay, that's at the left side. Now we're going to do the right side. So the right side is plus, now it's going to be the density of x plus dx. So this whole thing, x plus d rho x dx times dx times the velocity ux plus du dx times dx times the area, which is dy dz. Okay. So we'll stop there for now because it's 12:50. But what we're going to do is we'll see, okay, we did it in such a way that most of the terms cancel out and we end up with a fairly simple differential equation. So we'll hop back onto that on Monday and see what conservation of mass looks like in a differential world. Should be fun. So I hope you guys have a good weekend. Enjoy the sunshine that we have today. It's Michigan and it's still March. So don't forget about that. We'll see you guys on Monday. It's gonna, like a snowstorm is coming.
Yeah, but I was thinking the same, like, I'm feeling the sun's not. I really. Me too.